So we are making a small context switch from architecture to some math, and then back to architecture next week. So basically today I would like to remind you some basic ideas that we had when we talked about supervised learning, and extend this setting to what can be called as domain adaptation or transfer learning or semi-supervised learning. I will show you the similarities and the differences between these programs, and specifically I would like to talk about what can be tagged as domain adaptation. Okay, so basically we'll see that there are a few non-trivial things, elegant but non-trivial things that can be done. So just as a reminder, let's recall what we did when we talked about supervised learning. Okay, so in the supervised learning, we had some space that we called X. X, we call it an instance space. And Y, we call it a label space. Okay, so label, of course, is something that is typically, this term is typically used for classification problems, but we can also think of the label space as some continuous variable or maybe a continuous vector, and then we can freely use the same notions in regression problems. Okay? And I would like to adopt from the beginning the probabilistic view. Okay, so I will assume that there is some joint probability distribution Pxy on X cross Y. Okay? Which of course by Bayes' theorem, or actually but it's not even Bayes' theorem, it's just the definition of conditional probability, it can be factored into Y given X and P. Okay? So basically this conditional probability tells us how the labels are distributed given an instance. Okay? And if we have fully deterministic labeling function, we call it a target function, then basically this will be just a singleton distribution, okay, around its mean. Otherwise there will be some noise around it. That means that this is the prior distribution of the data that could be very complicated, and our goal in unsupervised learning was exactly to model that PX. Okay? Now we are assuming that we have some training set, let's call it S. Okay, we have a training set. It's a finite sample of xi, yi, drawn IIB from this pxy. Okay? So we have, let's say, we call this quantity N, capital N, pairs, labeled instances that we draw from this unknown distribution. Okay? And our goal is to find some hypothesis. Let's assume that we have some parametric family of hypothesis functions. Theta will be the parameter that maps from X to Y. Okay? So basically we would like to pick up H theta, or actually let's embody it by just picking up the theta, that will select the best hypothesis given the observations that we have in the training set, and hopefully we would be able to generalize to previously unobserved data drawn from the same distribution. Okay, so this was our setting. We said that we are minimizing some loss function that will be just a pointwise loss, so we take the average on the training set of some pointwise loss. Okay, and we minimize this with respect to theta. Okay, so this was our supervised learning problem. Okay, and we said that the choice of the loss is extremely extremely application task specific. There are pragmatic choices, of course, but there is a generic framework that we can adopt here. Basically, how to select the loss. So let's select this loss through the viewpoint of maximum a posteriori estimation. Okay, so basically what I can build a posterior probability So let's build the posterior probability of theta, given my my observations, right? So my observations is exactly this set S. Okay? This is my posterior. This is the posterior. Okay? So I'm observing S. I'm interested in inferring theta, in thinking of theta as a random variable, it's a random vector. And this is its posterior distribution, right? After I observe the data, okay, the training set. Now I can use Bayes' theorem to write this as a product of orbits. It's proportional to. It's proportional to obviously the likelihood function. Basically, just reverse the roles of theta and S times the prior, right? The prior distribution of theta. Okay. So the way I'm going to write it, I will write it as S given theta times Ps. Okay. Can you hear me?
P of theta, right?
P of theta. So of course this is called, in the Bayesian language, this is called the likelihood. And this is called the prior. Okay? So let me rewrite this. I will write this as the probability of the yi's given the xi's, and let me write theta here. Okay, just to emphasize that theta is treated in a slightly different way, right? It's the parameter of our hypothesis of our neural network times the prior of theta. And of course, in maximum a posteriori estimation, I'm interested in maximizing this with respect to theta. Okay, so I would like to maximize this over theta. Okay, makes sense? So this is standard map frame. Okay. Now, since the maximization of this term is equivalent to the minimization of the negative log, I can write this as the minimization over theta minus minimizing the logarithm of this posterior. I will also use the assumption that I sampled my training set IID. So basically this joint conditional probability will split into pointwise products. Of course, in the log domain it will become a sum, right? So it will be the sum 1 to n minus log what is written here, right? It's p theta of yi given xi minus log p theta. Okay? And I can think of this as of my loss that I'm minimizing. Okay, so if I'm in the business of minimizing the loss function, this is a loss function, right? So the first term, what we have here, essentially tells us how our neural network, how our parametric hypothesis, basically which probability it assigns to every label y, given the data x. Okay, so I can put a softmax layer on my neural network, and basically this will be the probabilities in the softmax layer for every y. And specifically, if I pick up the label yi, if I'm assuming discrete labels, then basically this will be the output of the yi's dimension in the softmax layer. Okay, so basically it's the class probability output. Okay, and this is of course again a prior. Now we have seen, so first of all, if I reduce this priori to a uniform distribution over theta, then it will simply disappear, right? And I will be back to maximum likelihood estimation instead of maximum posteriori estimation. And this is what we did when we talked about logistic regression, for example, right? Now, what we have seen, a heuristic that was called weight decay. Weight decay added a penalty, a regularization, an L2 squared regularization on the elements of theta, on the weights, essentially, right? So basically, we can interpret it as assuming a wide Gaussian distribution of theta, okay? If I put a wide Gaussian distribution of theta, the negative log of this density will become exactly the L2 norm squared, right? Of course, there is a more principled way to justify this weight decay regularization using more profound arguments, but at least we can see it from this framework as simply assuming a normal prior on theta. Okay, so I would like actually to do something more useful with this prior on theta. Okay, so basically this was our basic setting of supervised training. So let's now switch to a much more complicated setting of a problem, and actually we can think about several variants of this problem. So let's think about the following setting. I still have this space of instances cross the labels. Okay, so it's the pairs of instances and corresponding labels, and I will define a probability distribution xy. Of course, that is factorized into py given x times the prior probability of x, and I will call this some source data domain. Now, from this source domain, I will sample a sample set S containing xi, yi, I from 1 to n, again distributed ID from P. Okay? Now I will assume that I have another data domain. I will use the same instance and label space, but I will assume that it potentially has a very different probability distribution. Let's call it Q, QXY. Again, factorizable into QY given X times QX. And I will call this the target domain. And let's assume that we can access the target domain, we can sample from it, but we don't have labels. Okay, so the only thing I can sample is xj's, let's say m such samples, again IID, but now from the marginal distribution qx. Okay? And not from the journey distribution. So basically, if you think about it, this kind of problem, maybe in slightly different flavors, appears all the time in real life. So for example, usually labeling, obtaining labeled data is a tedious and expensive process, right? So for example, I might have some set of instances obtained maybe in some controlled environment in which labels are available, but then real world data in the wild, so to say, are slightly different or greatly different. So they come from a different distribution that I'm denoting here by Q. And unfortunately, I don't have labels there. So for example, I can give you many examples in classification, in regression problems. So suppose I'm doing, let's take a regression problem just to be more interesting. Suppose I'm doing, let's say I'm doing an image denoising neural network. Okay, so I would like to take a noisy image. I would like to crunch it and output some nicely looking image without noise. Okay? So I can address this as a supervised learning setting. So for example, I can build a very cool simulator that models all the processes that happen in my sensor, in my camera. So I'm giving it a clean image. I run it through the forward model. I create a noisy image. And then I'm training a neural network that, given this noisy image, will give me the clean image back. Okay? So I have perfectly aligned x's and y's. Y's in these cases have the same dimensions as s. But then I take real images with my real camera, and I have, of course, no ground truth clean image. Okay, so that is the target domain. And unfortunately, I cannot simulate all the effects very faithfully. So probably the real images will be simulated slightly different. Okay? So the P and the Q are not the same. Okay? You can also think about, for example, medical images. You might have something that you can simulate well, or you might be able to measure in the lab, but then you go to the real clinical setting, and in the clinical setting, you, for example, don't have ground truth. Okay? So this kind of problem is called domain adaptation. I would like to build a classifier that will be applicable to the target domain because I only care about the target domain. Okay? So somehow I would like to take advantage of this unlabeled set that still conveys a lot of information. It tells me how real data are distributed, but not a joint distribution. I only have access to the margin distribution. Okay? So I would like somehow to take as much information as I can from both worlds. Now, there is another flavor of this problem that is called semi-supervised learning. So in this case, P and Q are the same. I don't have target domain, I only have the source domain. But it might happen that I have zillions of data points, but most of them without labels. Okay? So I have two distinct sets. I have data points without labels and data points with labels, but they come from the same distribution. Okay? So can I take advantage of these unlabeled points in some way? Okay? So this is another setting. It is called semi-supervised learning. It can be thought of as a particular case of domain adaptation. Okay? There is another problem that is called transfer learning, which is slightly, first of all, this is a little bit of an abused term, so it's not really clear what it refers to, but usually transfer learning refers to taking advantage of knowledge gained in learning some task to perform some other task. So basically the adaptation will have to happen with respect to a different loss function or to a different task. Okay? And the data domains might be still the same. Okay? So basically, again, I would like to focus on the domain adaptation problem. I would like first of all to learn how to take advantage of the unlabeled samples, and second, I would like to see how actually to practically build a neural network that will be able to do this kind of transfer from a source domain to the target. Okay? And you can actually look at what people do in practice. In practice, you can say that if you don't have lots of data, you can train for some task. Let's say I'm training on ImageNet instances for doing visual recognition, and then I just take most of this network, remove the last fully connected layers, let's say, and I put some other classifier and optimize this with respect to a new task on new data without touching this big portion of the network with lots of parameters that essentially create an embedding, create a representation for my images, hoping that the representation that I learn on a different task will somehow be helpful for a new task. And surprisingly, this works without real understanding why. Okay? So I would like to show you something slightly more principled, how actually to take advantage in a more rigorous way of the unlabeled samples. Okay? Yes?
Can you assume any assumption about if you have like overlapping between S and T? Any assumption?
Well, so there will be some tacit assumption. Of course, if P and Q are completely distinct, then basically this set P of unlabeled data will be of little use. Okay? So I will have some, there will be some parameter that will essentially, so essentially I will get two loss functions. Okay? And there will be some parameter weighting one loss with respect to the other. And that will come from, basically, from some assumption about the separability of classes in the target data. So I don't have access to the classes, but I can still put some constraints on this separability. Okay? So just look at this. This is a very generic way of formulating the loss function, but just pay attention, it has two terms. The first term is the likelihood term, the second term is the prior term. So first of all, convince yourselves that the prior term can gain no advantage from unlabeled samples. Right? The prior term, the likelihood term, needs both x and y, right? And we don't have y's on P, on the target domain. So the only place where we could potentially make any use of the target domain of the unlabeled set is the prior. It's the prior of theta. Okay? So we said that the trivial thing, and actually this is a very justified choice, is to say that we assume uniform distribution of theta, we just remove this prior probability and we end up with a maximum likelihood estimator. We can put some heuristic, some L2 regularization that has, again, more profound meanings, but this is an arbitrary choice of a prior. Let's put some non-arbitrary, slightly more motivated choice of the prior that will take advantage of it. Okay, so this is what I would like to show you next. Yes.
Maybe I misunderstood at the beginning, but theta is the parameters of your neural network.
Yes.
So basically, if you have a neural network, then so theta is like the weights and biases.
Let's say it is 20 million weights and biases.
Yes, so how can you say anything about the probability of the weights and biases?
Okay, let's see how we can do it. So basically, I would like to somehow intelligently incorporate this data. So I have only, so do you agree with me that I cannot incorporate them here? They are useless here. I don't have whys.
I'm asking what does it mean, the probability of something that is...
The parameters, so of course it is parameterization dependent, but will we construct some measure that will be based on conditional entropy that is parameterization independent. Okay? And it will lead to a posterior, to a prior on theta.
What I know from maximum a posteriori is when you start to like estimate a class based on a label based on data, and you take into account the priori probability of said label. This is not what you're doing here. What you're saying is you take into account.
I'm saying I would like to prefer some classifiers, some hypotheses over other hypotheses based on the unlabeled data. Okay, this is exactly what prior probability means. Okay. Again, so it's prior on theta, prior on h, not on s. Okay. Okay. So let's see.
Not on y.
Pardon?
Not on y.
And not on y, of course. Okay. Yeah. So let's. So first of all, again, there is quite a lot of study in the literature, in statistic literature, for example, in learning literature, both from the theoretical and from the empirical perspective. Basically, how much the unlabeled data set can contain information useful for this domain adaptation task. Okay? And basically, we can actually show that this information content decreases as the classes start overlapping more and more. So basically, ideally, if the classes are well separated, we can take more advantage of this unlabeled data set. Okay, so again, there are quite rigorous theoretical justifications to this hand-waving claim, and there is, of course, a wealth of empirical studies that confirm it as well. So let's do the following. Let's quantify how well the classes are separated. Okay, so basically saying how well the classes are separated is equivalent to saying how much uncertainty we have in a label given a means, right? Of course, everything depends on our parameter theta, so I'm not going to write it as a conditioning variable. I'm going to write it as a subscript, but essentially it has to be on the right side of the conditional probability. It has to be one of the conditioning variables. I just want to remind you that even though we treat it in the Bayesian framework as a random variable, it's not exactly the way we would like to treat it, right? So that's why I'm writing it in the subscript. So essentially, I would like to quantify how much information my instance reveals about the label y. Okay, so basically, how much uncertainty remains in y given x. Okay, and there is a very clear information theoretic measure that tells me how much uncertainty remains, and this measure is called the conditional entropy of y given x. Okay, So let's write this conditional entropy. I'm writing this parameter theta. Theta should be written here as well. It's also one of the conditioning variables. So essentially it will be the expectation, or the negative expectation. The negative expectation of log p theta. It's exactly that probability there. Y given x. Okay, so let's write it explicitly. I can write it as an integral with respect to x. Okay, and sum over all the labels. Okay, so I'm assuming that I have a discrete label space. Otherwise, I will need to write an integral over all the labels with some density on the label space. It will be an integral on basically on space x. Integral of p theta y given x log is negative log p theta y given x dqx, because I'm taking x's from the target distribution, of course. And pay attention that I'm not using any assumption on known measure on the known joint measure on the target space. Okay? Yes.
Isn't the integral supposed to be qx and the differential dx?
Well, there are different notations, but it's integral with respect to the measure with the measure q. Okay? So it's a Lebesgue integral with respect to the measure q, if you want to be completely formal, right? Integral over the space x. So basically, this is the definition of conditional entropy, of course, and I'm summing over all the labels. Of course, I don't really have access to the measure q. I have access to a finite sample, sampled from that measure. So, of course, I'm going to approximate this integral by a finite sum, okay, by a sample average instead of a true expectation, which is still enough. Under the same assumptions, we said that we can generalize from a finite sum, right? So it will be minus 1 over m, sum over y, sum over j, p theta yi given xi, sorry, no, it's not y given xi, log p theta y given x. Okay? So this is my final sample estimate of the conditional entropy. This conditional entropy again tells me how much uncertainty I have in the labels given the instance. Okay? So basically it quantifies the class separation. So some choices of theta will give me better, will give me lower uncertainty. Some selection of theta will give me higher uncertainty. Okay? So basically I would like to put some bound. Let's say so basically let's bound this quantity. Let's take an expectation of this quantity over all thetas. Okay, so I will take the expectation of this over all thetas. Of course, this expectation is computed with respect to the prior on theta. Okay. So let's think of theta as a density. Okay, so I write it like this, like a standard Riemannian integral. So basically, this quantity tells me how much uncertainty I have on average in the labels, and let's bound it by some parameter epsilon that I will have to choose. Okay. So basically, I still need to select my prior distribution of theta, but I would like to select it subject to this constraint. Because I know that if I am not satisfying this constraint, basically I have a lot of overlap between the classes, and I know that basically the usability of my unlabeled set is low. Okay? So basically I would like to put this as a constraint. Okay? Now, if I'm putting this constraint, now what would be what would be basically the most natural? So suppose this is the only information I know about my prior probability on theta. Okay. So what would be the most meaningful, or at least in some way, what would be a principled way to construct a prior distribution? Okay. So let's assume I have no information whatsoever on p theta, on the prior. What prior would you assume? Uniform, right? So uniform is by saying that I would not like to introduce any biases into my calculations, right? So take a uniform distribution. So a uniform distribution has a very particular property in terms of entropy. Maximum. Okay? So here, I don't want a uniform distribution anymore because I have some constraints, I have some knowledge. This is my knowledge about p theta. So let me write it as a variational problem. I would like to maximize the entropy of theta subject to this constraint. Okay? So give me a probability distribution of theta that satisfies these constraints and maximizes the entropy of theta.
You can take Gaussian distribution and turn it into sigma.
Well, the Gaussian distribution is not exactly the most generic type of distribution, right?
Gaussian mixture distribution.
Okay, so I would have something exponential, but with some intricate dependence on theta. Okay, so let's see. It will be a very, very easy problem. Okay, so basically, so this is the only knowledge that I would like to take with me into the definition of p theta. So let's write the following variational problem. I'm maximizing over p theta the entropy of theta, obviously with respect to this distribution, subject to this constraint. Obviously, I have a trivial constraint that the integral of p theta has to be 1. Right? It's a probability distribution. Let's write another obvious condition. So it's a variation problem. I'm looking for a function minimizing this functional subject to these constraints. Okay, so let's rewrite it. Let's rewrite it as so first of all, entropy is defined as negative expectation of the log. Let's take positive expectation of the log instead of maximum right minimum, and introduce Lagrange multipliers to write this as an unconstrained minimization problem. Okay, so the unconstrained minimization problem that I'm going to get will be this: minimize over p theta, integral p theta log p theta. Okay, this is the entropy. Let's write it as Riemann integral. Okay, plus lambda, the Lagrange multiplier of the first constraint. Let's write what is written there. Integral over p theta h theta y given x minus epsilon plus mu, and I have the other constraint. Okay? So I would like to solve this minimization problem. I can write basically what is written here. Well, so basically my optimization variable is p theta. Integral is a linear operation, right? So I'm doing some hand waving here. So if you want to be completely rigorous, just write down the Euler Lagrange equations for this function or solve them, and you'll get exactly the same result. But you can say, let's just fix theta, treat p theta as a scalar unknown, and minimize this function with respect to p theta, and do it for every theta.
That's Euler Lagrange.
Exactly. So in this case, it's exactly the same. So let me write this problem as, let me write it as p log p. I'm fixing theta. Okay, so fix theta plus lambda p h. Let me write it as lowercase h. It's exactly h at point theta minus epsilon plus mu plus mu p minus. Okay? And I would like to bring this to minimum over p. So it's obvious, you take the derivative with respect to p, you equate it to 0, and what you're going to get is that basically you will have here p prime, it will be p prime log p plus p prime over p, and these two cancel out, plus lambda p prime h plus mu p prime equals 0. Okay, so I can write here as p prime log p plus 1 plus lambda h plus mu equals 0. Okay? Okay? So I would like to equate these to 0. So I would like what is written in the parentheses to be 0, from which I get that the log has to be minus what is written here, or p has to be e to the power minus lambda h times e to the power minus mu plus 1 plus 1. So this is just a normalization constant. So basically what we can say that p theta has to be proportional to e to the power minus lambda h theta y given x. Okay? So this is my prior distribution.
And that is the exponent of u is the partition factor.
Exactly. So the lambda comes from my epsilon, right? It's the Lagrange multiplier associated with the epsilon. Every choice of epsilon will yield a different lambda.
May I just say this looks like the solution to a canonical ensemble.
Sure. Of course, there are many. Of course, anything that relates to entropy has lots of analogies in statistical mechanics and in information theory. There are many relations. So you can think of lambda as temperature, if you will. Yeah. So of course, 1 over. So let's now just rewrite this prior distribution in terms of this empirical estimation of h theta. So let's put the two losses together. Let me write them directly as a single loss function. I have essentially two terms. So let me write loss of theta. So the first term, I already cancelled it, but it was, of course, given by the likelihood. It was minus 1 over m, sum I from 1 over n. It was the labeled training set, yes. 1 to n, log p theta, yi given xi. Okay? So this is the likelihood computed on labeled data. Minus, so it will be e to the power of that thing, but of course I have log, or minus log of that thing, right? Because it's negative log of the prior. So it will be simply plus or minus. Plus or minus, it should be plus, right? So the log is plus, the negative log is plus. Plus lambda over m, sum from j to m. And what is written here is this estimation of the entropy, sum over y, p theta y given xj. Here it's xj, of course. The sum is over j. P theta y given xj log p theta y given xj. Okay, and this comes from unlabeled data. Okay? So in label data, we have specific labels. So if we evaluated log p theta at yi given xi. Here we don't have labels, so we sum over all the labels in the label space, and we evaluate the entity, right? We evaluate p theta times log p theta. Okay? So I'm convinced that this is a more principled way to incorporate data from another domain than just saying throw some layers and train a fixed part of the network on new data. Okay? Yes.
In some way, you have some approximation of your function, some current classifier, and you use that classifier to give you labels on unlabeled data.
Sure. And that's exactly what I mean.
Okay, cool.
Right? Well, I don't have any other source of labels.
No, and you're using those classifications to a loss on your classifier.
Yes. Well, I mean, I think this is the best I can do. So there is one remaining thing. So this is my loss function that I would like to use. It incorporates both data sets. It can of course work for the domain adaptation and for the semi-supervised setting. But let's say a few words about the hypothesis itself. Okay, so here I'm training one hypothesis, h theta, right? That minimizes this loss, and I would like to apply this. Essentially, I would like this hypothesis to perform well both on S and on T, both on the source data and on the target data, right? Because it's just a single set of parameters. Okay. Now there is a paper from Joshua Benjo a few years back that argues, actually formally proves, that even if you assume that you train a classifier to perform, basically to give a very low amount of label disagreement on S and on T. So suppose you have access to some ground truth labels on T. So you train your classifier and it has very small amount of disagreement on these two distributions. And even if you assume that P y given x equals to q y given x, so essentially you're assuming that the prior distributions of x's might be different, but the labeling process is the same. This is what is called, in part of the literature, is covariate shift. It's a terrible, terrible term. Because in some literature it is implied to mean just the opposite. But let's not use it. So you assume essentially that the labeling is the same, you might have the instances themselves distributed differently. So even if you assume that your classifier produces small amount of label disagreement, and you have this assumption, there is no guarantee that that single hypothesis will perform well the domain adaptation task. So it will perform well both on S and on T. So you need to assume some relatedness between the two distributions of S and T. So for this reason, we should probably build two different hypotheses for the source and for the target, right? So since we are fixing the same parameter, what else can we do? So basically we have the same network topology, basically it's constructed exactly in the same way. We have the same weights, the same biases for the network. But now we want from this network to produce two different hypotheses. One working on the source domain, and another one that has a different input to output map that works on the target domain. Okay? What can we do? So one trivial thing, and basically these trivial things can be explored in the literature. So one trivial thing would be to say, okay, let's transform the input distribution in such a way that the distribution of the source and of the target match. Okay? And of course it's difficult to make a generic transformation of the data, so let's just make a linear transformation so we will match the first and the second order moments. Okay? Obviously the distribution will not match unless they are Gaussian, which there is no real sense in assuming that any reasonable real data will come from a Gaussian distribution. So what we can do next, we can try to apply this transformation in the intermediate layers as well. So basically you are not only aligning the inputs, you are also aligning feature maps at different levels in the representation hierarchy that the network learns, right? So basically you are applying this linear transformation that matches the first and the second order moments, let's say, at every layer, and therefore you get a very intricate transformation, nonlinear transformation that aligns the two distributions. So it resembles a very commonly used practice in your batch normalization, right? So this was exactly the purpose of batch normalization. We use batch normalization to normalize the distribution of the activations coming into the input of every layer of the network. So let's just briefly remind ourselves what we have in batch normalization and use a very similar idea for our purpose of domain analysis. So what I'm showing you, by the way, is something that is really cutting edge because it's more or less 1 or 2 years old. So it still hasn't become common practice, but first of all, I'm very enthusiastic about at least some rigorous justification of what is going on there. And second, it looks to work very well. So I think it's here to stay. So basically, in batch normalization, what we did, batch normalization was a layer that was applied individually to every activation of some layer inside the neural network, especially it's useful for deep layers. It had two parameters, beta and gamma. So essentially, so suppose we have x, let's denote it by z, let's stick to z. So suppose I have an activation z that comes into the input of the layer. Let's write the parameters as subscripts, and z will be my input. So what I'm going to do, I'm going to subtract the empirical mean that I estimate on my batch, and will divide by the empirical variance that I estimate on my batch. Okay, so of course, this is a batch estimate of this, and this is the batch estimate of this. Okay? So in this way, I have a normalized, at least in the sense of the first and second order moments, I have a normalized distribution of this variable at every batch. So this subtraction is done on the batches. And then I will reintroduce some scaling and some shift. These two parameters, gamma and beta, will be learned for every batch normalization unit. Okay? So this is what batch normalization was doing. Now we can do exactly the same. We can do exactly the same trick for domain alignment. So let's call this a domain alignment layer. Let's call it VA layer, and it is administered into the network exactly in the same way batch normalization is done. But basically, the domain adaptation layers or domain alignment layers will basically come in couples. There will be one layer that we are employing when we are applying the network to the source data, and there will be another layer that does a different transformation that will be employed for the target data. In this way, I have two potentially very distinct hypotheses that share the same network topologies, share the same set of parameters, but they are distinct in this domain alignment layer.
So how many domain alignment layers you have to add to the network?
Well, here comes the alchemy of this domain. So I don't have an answer basically how to build from some principles how to build a network topology, network architecture. Right? So basically, in the same way, I cannot tell you what is the exact recipe of how many batch normalization layers to put. Same story goes for domain alignment. But you should put quite a few, different points, different depths of the network.
And how you do the training? You have a network that's already trained for the target?
No, you're training simultaneously, so you're minimizing this loss, right? So you both have labeled source data and unlabeled target data. Now, you will see that there will be a parameter that tells the amount of mixing between the source and the target distributions. And basically, if you can select it from individual training in which you can train essentially just on one just on one source of data.
So I'm missing something here. In the beginning of the class, you said that you want to gain from the knowledge that you train the network for the source domain.
Or I would like to gain from both, right? But the only difficulty with the target domain, and it's a major difficulty obviously, is that I don't have labels. So I need to do a supervised training task that has to fit well target domain data without having any access to labels on the target domain. Okay? That's the main challenge in the domain adaptation. Okay? So we have a great loss function we even can justify mathematically, but now let's see how can we produce two different functions. One for the source domain and another for the target domain. I didn't prove to you that a single function will not do the job. It's not guaranteed to fit well for both source and target. Okay? But basically, it's a claim that has been proven mathematically. So we must create two different functions. Okay? And I don't want to co-train two different sets of parameters. It would be very expensive. So I would like to train the same parameters and just do the adaptations of the distribution. Okay? So basically what I will assume, so assume that somewhere deep in the network I have some activation. Let's continue calling it, well, I won't call it Z. Basically because I have this activation on source data. Let's call it S, let's call it source activation. And let's call the corresponding activation when I'm giving target data, let's call it T. This is the target activation. Okay, so I have one feature map at specific spatial location in some layer in the neural network. When I feed it with data from the source domain, I'm getting a random variable S that is distributed somehow. Let's call it distribution P. And this P is distributed according to some distribution Q. Okay? Two different distributions. Okay? So let's create two mixture distributions. I will take a parameter alpha. P alpha will be just alpha P plus 1 minus alpha Q. And Q alpha will be just the opposite. Alpha Q plus 1 minus alpha P. Okay, these are the two mixture distributions. So basically, I would like to estimate, like a batch norm, I'm going to estimate mu and sigma on the batches, but now the batches will be contaminated by data from the other domain. Okay? So I'm going to construct two twin layers. Let's put alpha as a parameter. Two twin layers for the classifier, for the hypothesis that I'm going to apply to the source data. So this is for the source h theta. I'm going to apply this transformation. I'm going to take my S, I will subtract from it mu computed with respect to P alpha and divided by sigma computed with respect to P alpha on my batch. Okay? And for the target hypothesis, I'm going to apply, of course, T, and I will compute mu and sigma with respect to Q alpha, and here with respect to Q alpha. Okay, so basically, I'm doing a different transformation. So, since I'm doing it in many intermediate layers, I'm going to get a completely different set of functions. Okay? So basically, I would like to train theta, minimizing this loss. Since I'm introducing these domain adaptation, domain alignment layers into the network, I'm going to, so the smartest thing I can do is to put alpha also as a training parameter. So I will train for theta and alpha, so that basically the need to minimize this loss will decide automatically how much mixing I need between the two distributions from the two domains. Okay? I can keep alpha to be 1, and this essentially means that I'm working with each domain individually, and this has been done in what is called adaptive batch normalization. It's exactly adaptive batch normalization. And if I allow alpha to be lower, this is called, it's a recent CVR paper called autodial. That essentially extends on the adaptive batch normalization. Okay, so basically, using an idea that is very similar to batch normalization, we are creating, essentially we are training simultaneously two distinct hypotheses with the same network structure and the same set of parameters, differing just by disalignment layers. One is applicable to the source data, another one is applicable to the target data, and we are minimizing the loss that takes both the source and the target data into account.
What do you mean that P is tilde S?
Oh, so it's reads the other way around. It's S distributed, let's go like it this way. So S is distributed according to some measure P, and P is distributed according to some measure Q. Okay?
What does source activation mean?
Pardon?
Source activation is the...
Well, so it means it's the same activation on the network fed with the source data.
And the source data is delayed.
Yes, exactly.
But how do you get the P and Q? Can you calculate it from somewhere?
Well, of course, I'm estimating it on the batch. I'm doing it on every batch. Same way I did for batch normalization.
Ah, okay.
Okay. Questions?
How do you choose alpha?
Oh, so I can either fix it to something, or the best thing I can do is actually to put it as part of the learning parameter. It should be between 0.5 and 1. Right? So I can just put trivial box constraints by using project and train alpha for the entire.
After you finish this process of training, I would expect that the accuracy of the source data is lower than if you would not have had that regularize on the unlabeled data, but your accuracy on unlabeled data, the tested accuracy, should be higher.
Well, of course. So it's some trade. Of course, it will. So if you don't put any prior on, if you don't put any prior term, you're going to do excellent job on the source data, but you might be doing a terrible job on the target data. Right? So basically, the second term when you loss is essential to get good performance on the target data. Okay?
How the topology of the network is look like? Because you put this in the middle between two layers.
Well, you put it exactly the same way you put batch norm.
Yes, but batch normalization it's the same for all the network. Here you have one normalization for P and one normalization with Q.
Sure.
So it's
so
like
basically you have two versions of the network. One, which you are evaluating simultaneously, right? So one version works on the source data, another one works on the target.
So you have two networks, like you're training two networks.
But they share the same parameters theta. So all the millions of weights that you typically train are shared.
Yes.
Okay. So the only parameter that you train here is perhaps alpha if you train it, or it could be fixed. Okay. So if you train alpha, it's like in batch now. You have a very small set of parameters that you have to add. Okay.